Hello and welcome to this lecture video. Today we will be discussing critical refraction and head waves. So refraction happens anytime you send energy, energy, into the earth and it meets an interface with a different where the material underneath has a different wave velocity than the material above. When that happens, the wave will refract at that interface. The refracted wave travels along that interface. So specifically on this slide, we're discussing critical refraction, and that means that the lower medium has a higher velocity, and so the energy bends away from the normal. And if that energy came in at just the right angle, it will bend 90 degrees and travel along the interface, and we call that critical refraction. Refracted waves travel along the interface at the speed of the faster medium. Here we have the critical angle at which that is going to occur. Now, the critically refracted wave creates oscillations in the upper medium, and these oscillations will actually propagate upwards towards the surface. So if we were to draw that as ray paths, it could look like this. The ratio of the velocities of the upper and lower levels is the same, whether you're coming into that critical refraction or going out of it. So that means that the angle in both cases is going to be the same. Another thing to note is that critically refracted waves are created at every point along the boundary. This is explained by Hugos Principle, which treats every point along a wave as an initial point of a wavelet capable of generating new waves. Hugos Principle is sort of shown in picture format here, where basically I've just chosen a few points along the line to show you that you can imagine energy is spreading out in every direction from those points, and you could be drawing refracted rays up from all of those points along the whole path of the ray. We're not going to go into Hugos Principle anymore in this video, but it is discussed in a little bit more detail in a video a little farther down in your lesson. So the next thing I want to talk about is the head wave, right? So head wave is just a name that we give to this critically refracted waves. Head waves are actually the only refracted waves that can return to our instruments. All other refracted waves are lost to the depths, right? Only if they refract to the interface where they're capable of generating wavelengths that can come back to the surface, only those are we going to be able to detect. And in fact, if we have instruments far enough away from our energy source, then eventually our instruments are going to be capable of detecting the head wave, because eventually it will arrive before the direct wave. And that's because the whole time that it travels along the boundary, it's traveling at the velocity of the deeper layer, which is faster, while the direct wave is always traveling at the velocity of the upper layer, which is the slower velocity. Okay, another thing to note is that the very first critically refracted wave is actually also a reflected wave, right? Because reflected waves come down and bounce off the interface at the same angle as they hit it, which is the same thing that this critically refracted wave is going to do. So they share one point in common, and after that, the critically refracted wave is actually going to be faster than the reflected wave in all cases, because it will. So after that, the refracted wave will be faster than the reflected wave in all cases, because it will have spent some time traveling along that boundary at the speed of that faster, deeper layer. Again, because it travels faster down there, it will eventually be able to arrive back up at the surface in less time than it takes the direct wave to travel along that surface to an instrument. So just to reiterate, the first head wave is actually a reflected wave at the critical angle, But following that, because the critically refracted wave will have spent some time traveling at that faster speed, it will always arrive earlier than the reflected angle, and at some point it will even arrive earlier than the direct wave. Now, the first location along the profile that the critically refracted wave can be identified, that distance is actually referred to as the critical distance. Any distance shorter than that and you're not receiving any critically refracted energy. And then at some point over here, you're also going to have the crossover distance, and that's the distance at which the refracted angle arrives earlier than the direct wave. All right, I hope that helps with understanding how these waves interact with the ground and our instrumentations. And in the next video, we'll learn more about how to take this and learn something about the ground beneath our feet. Thank you. I hope this was helpful.